morning. In today's class, we will discuss further on impulses or impulse generated from a blast wave driven by an explosion, point 1. After that, we will also try to take a look at something like missiles, maybe fragments, shrapnels which are generated by an explosion, missiles from explosions, and if time permits, we will also take a look at craters which are formed at the site of the explosion. Let us take a look at impulses. We already defined what an impulse is. To clarify further, let us take two examples. Let us say I have a house, let us say a small house over here with a window pane over here, or let us take a man who is standing over here. Let us assume that there is an explosion occurring some distance away from the house, in front of the house, and then you have blast waves which come and hit the house as it is. What happens? Or a blast wave comes and hits the front of the human being. Let us say that the area is A, the frontal area is A at which the blast hits it. Therefore, what happens when the blast wave hits the house? That means the ambient pressure, let us say, is P 0. Let us have a plot of pressure as a function of time. The blast wave comes and hits the house, and therefore, I have a pressure, that is the pressure from P 0, that is the ambient pressure, rises to a value of P s. Mind you, when the blast wave hits it, you have something like a pressure could be higher because the blast wave gets reflected. We will take a look at the reflected pressures tomorrow, but if I were to look from the side view, that means I am looking at the blast wave as it is progressing. I am looking from the side, I take the pressure rise across the blast wave here, and what happens? The blast wave further propagates, the pressure decreases, and this is the type of pressure decreases. And when the pressure decreases because of the change of pressure, I have a wind, maybe because of the momentum the pressure could even go to negative values, and therefore, I have a duration over which the pressure is higher than the ambient, maybe over a duration of t plus I have pressure higher than the ambient value P 0. I have a duration, let us say t minus, over which the pressure is less than the ambient, and therefore, if I say that the area of the house or area of the person is A, then at any time t, let the pressure be P t. Therefore, the pressure difference which the person experiences P t minus P 0, and if I multiply this by the area, I get the force, and the value of change of momentum is equal to, let us say, this is the force which the body experiences, and this force is a variable. I want to find out what is the impulse, and what is the impulse is the change of momentum. Rate of change of momentum is the force, and therefore, I can write the impulse which the body feels as equal to P t minus P 0 into A, as it is integrated from 0 over the particular duration, let us say t plus for the positive impulse, because in this case the force is higher, the building is sort of dragged in this particular direction because of the change of momentum. In this case, the building comes towards the front, I have negative impulse, that is minus is equal to, I have the ambient pressure minus P t into sort of d t into area. This also is integrated with respect to d t over here. I have the positive impulse, I have the negative impulse, and what we defined yesterday was, we said, well, I can talk in terms of specific impulse which is equal to the impulse divided by unit area, and therefore, we write the expression for specific impulse which is positive in the positive specific impulse as equal to 0 to t of P t minus P 0, which is the ambient pressure into d t over here. Similarly, I also have the value for the negative specific impulse. Therefore, specific impulse is different from the impulse in that we are talking of impulse per unit area, and this is equal to, these two things are equal to I divided by A, I plus divided by A is I s plus, and if I talk of I s minus, I minus divided by A is I s minus. Having talked of specific impulse, I think it is also necessary for us to look at the units of the specific impulse. Well, the unit of impulse is equal to change of momentum, and what is change of momentum? You have mass into velocity is the change of momentum, that is kilogram meter per second. I can also write this as equal to kilogram meter by second square into second. Kilogram meter per second square is Newton, this is second, and therefore, impulse could also be written as Newton second. In fact, this comes directly from this integral, therefore, let us take a look at this integral. This is force in newtons into time, which is Newton second. Therefore, we can say, well, the unit of specific impulse should be Newton second. Since I am talking per unit area, the unit should be Newton second, which is for impulse divided by area Newton square. This is the unit for the specific impulse, let us say positive, let us say negative. In general, most of the blast waves, the damage is done by the positive impulse, because the magnitude of the negative impulse over here is always much lower than this value. Therefore, we look for damage point of view looking at the positive impulse alone, and most of the literature gives values for the positive impulse, but we must also remember that the negative specific impulse is also important. Let us take this example again of the house. Let us say I have the blast wave coming, hitting this over here. Let us say this is the window pane of this house, which I now show here. And what happens? Because of the impulse and the sudden rise in pressure, let us say that the window pane gets shattered, and therefore, initially the impulse is acting in this particular direction towards the house, and therefore, but it takes some time for the window to break, and when it breaks, the window is subjected to the negative impulse. It takes some time for the window to break, then it is subjected to a negative impulse. Therefore, the fragmented part of the window falls towards the explosion site rather than falling along the explosion inward. That means, the effect of the negative impulse, supposing I have a window pane like this, something gets ruptured, the blast is travelling in this direction, the failed window or the fragments fall in this particular direction, and this is how the negative impulse also influences it. We will basically look at the positive values of the specific impulse and thereafter calculate value of the impulse, which is just the multiplied by the particular area. Having said that, let us also take one more look. We are talking in terms of maybe the pressure distribution, which gives me the value of impulse, and the impulse is over a particular time over which it is taking, over which the blast wave is moving, or over which I have the positive contribution of pressure. Now, there is something which we must not forget. When we are talking of these impulses taking place, let us take a look at what causes this impulse. Is it possible to write the value of impulse? This is in units of Newton second per meter square. We told ourselves initially there is a rise in pressure, it comes down with respect to time. And what did we say? That the rise in pressure, that is the pressure behind the blast wave, we wrote it in a non-dimensional form as Ps minus the ambient pressure divided by the ambient pressure. Can I also write the value of the impulse instead of carrying a unit like Newton second by meter square? Can I also express it in a non-dimensional form? Therefore, we again take a look. Yes, my value of the specific impulse, which let us say positive value, is given as Newton second by meter square. Now, I want to make it into something like a non-dimensional form, and therefore, I find that I have a value like Newton per meter square, and the easiest way of getting rid of this would be to say, well, I have Is plus. If I were to put it in terms of the ambient pressure, well, I get Newton second by meter square. Now, I get Newton per meter square in the denominator. Therefore, this goes, but still I am left with a second, and easiest way is if I multiply the numerator by a velocity and denominator by a distance. Well, I have the sound velocity in the free stream medium. I know that the intensity of my pressure spike here depends on the value of the explosion length, because that tells me how strongly it is, how strong or how much energy I am driving in. Therefore, if I take a look at this, I have meter per second, I have something like meter here, Now, if I cancel, I get meter over here, I get meter over here, meter and meter get cancelled over here, the Newton and Newton get cancelled, second and second get cancelled, and this becomes a non-dimensional unit for the specific impulse. And this non-dimensional unit is represented by Is, let us say plus non-dimensional, which is equal to exactly what I have written here, the specific impulse with units divided by this divided by P0 ambient pressure into the explosion length. We want to derive the expression for this and see how it affects the building. Maybe we will do this when we are assessing the damage. But to be able to get a value for non-dimensional specific impulse, all what we do is, well, we know when we have a strong blast wave, the magnitude of this as expressed as Ps divided by rho 0 Rs dot square, and the changes in density and the changes in velocities associated with this are not dependent on the Mach number. We also note that the gradients behind it will be similar, and using, therefore, I can write for a strong blast wave, that is strong blast assumptions, that means Mach number is high. I am talking of Rs by R naught, which is somewhat near to my center of the explosion. For the strong blast assumption, I can therefore get it explicitly, and the expression, if I put the gradients and all down, comes out to be Is plus is equal to 0.322 divided by Rs over R naught. This is the way the non-dimensional impulse is changing with Rs by R naught. In fact, if you do a strict analysis, you will find that the velocity behind a blast wave, if I do a self-similar analysis or I write the conservation equations in differential form and evaluate the velocity changes behind a blast wave is sort of linear, and therefore, you get the values of Is plus as equal to 0.322 divided by the scaled, that is the scaled value of the distance Rs scaled by R naught, and this is non-dimensional, and this in fact is true for strong blast. That means, when I talk of the values of Ps between, let us say, 2 to 3 to something like maybe 2000 atmospheres or so, when I talk of fairly high values, I get this particular value. I have not derived it, I just use this value. There are a lot of correlations available in literature for different types of explosions, how the non-dimensional specific impulse will behave. This is for a strong blast assumption. Similarly, if I have an assumption which is, let us say, a weak blast, that means I have something, what should I say now? If I talk in terms of T versus Rs, I start with a strong blast assumption. That means, in the strong blast assumption, I am in the near field, wherein Rs by R naught is less than around 0.4 to 0.5, or let us say less than around 0.35, for which this expression is valid. When I am talking of the weakened case, namely when the blast has gone to the far field and it is the Mach number is not that high, then in that case maybe I use in the far field, I use the acoustic approximation, and what I get is Is plus is equal to, I get gamma, let me get you the exact expression. Is plus is equal to gamma into gamma plus 1 into A cubed divided by Rs over R naught in the far field. The value of A, which is a constant, varies between A is equal to 0.23 to something like 0.246. There are, as I told earlier, there are a number of values of the non-dimensional available for different types of explosions, but I think we will just examine these two for strong blast case and in the far field. Therefore, I think this is all about the impulses, and let us do a problem such that we are very clear how to calculate the impulse, and I do this simple problem. Let us take this problem of, let us determine, let us say, I say determine the impulse, that is the value of the positive impulse, when I have an explosion in which, let us say, 100 megajoules of energy is released, that is an explosion in which 100 megajoules of energy is released at a source in an ambient pressure, wherein the ambient pressure P naught is equal to, let us say, 10 to the power 5 Pascal, that is equal to 1 atmosphere over. I want to determine the value of impulse at a distance of, let us say, 2 meter away from the site of the explosion. Therefore, what I do? I have to calculate this value. Well, my RS is equal to 2 meters away. The energy is 100 megajoules, therefore, I know R naught is equal to E naught divided by P naught to the power 1 by 3. Well, I am still in the framework of the spherical explosions. I assume that the explosion is spherical, of spherical geometry. Therefore, this gives me 100 megajoules into 10 to the power 6 divided by P naught, which is 10 to the power 5 over here. Pascal, be careful about units, Newton per meter square, this is Newton per meter cube, this is equal to 1 by 3, this is equal to 10 over here, I have 1000 to the power 1 by 3, so much meters, which is equal to 10 meters. Therefore, the explosion length for the energy deposited at 100 megajoules in an ambient pressure of 10 to the power 5 Pascal is 10 meters. I am interested in RS by R naught, that is RS is 2 meters, 2 divided by 10, which is equal to 0.2. We know from our earlier discussions that this is the near field in which the blast wave is strong, and since blast wave is strong, I am justified in using this particular expression, and therefore, I now calculate the value of the non-dimensional specific impulse. Let us calculate that value. Non-dimensional is equal to 0.322 divided by the value is 0.2, which is equal to 1.6, that is 3.2 divided by 2, say 1.61 is the value of the non-dimensional specific impulse. But this is non-dimensional. I wanted to calculate the value of specific impulse, and specific impulse IS non-dimensional is equal to IS plus into, let us put down, it is equal to the sound speed divided by the value of P0 into R0. We have the ambient, which is equal to 1 atmosphere. Let us say that the temperature is ambient, the sound speed in ambient is around 330 meters per second. This should have been given to you, and therefore, I get the value of IS, this positive specific impulse, as equal to 1.61 into the value of pressure is 10 to the power 5 Pascal. The value of R naught we determined as equal to 10 meters divided by the sound speed, which is 330 meters per second, and therefore, the value of the specific impulse comes out to be 1.61 into 10 to the power 5 divided by 330 into the value of R naught is 10 over here, this is equal to 4080 Newton second by meter square, this is the value. And depending on the frontal area, if the frontal area is, let us say, 0.5 meter square, the value of the impulse is equal to the value multiplied by the frontal area, and this is how we calculate the value of the impulse. Therefore, what is it we have done so far? We did not get into details of derivation of this, because we already know for a strong blast it is like this. Maybe if I am looking at a distance far away, therefore, I need to first calculate the value in the far field, and if I know it is in the far field, I use different expressions for the value of the non-dimensional specific impulse. In this case, I use this because I know it is in the near field. In fact, there are plots for the non-dimensional specific impulse, like I show in this particular slide. I show the non-dimensional positive specific impulse as a function of RS by R naught. It varies over here, and to be able to apply it, first we go back to what we did in the last class, namely the overpressure. We find out at the RS by R naught what is the type of overpressure, and find out what is the shock pressure. Find out for this type of pressure what we have, whether what type of correlation to use for the impulse, and use the particular correlation, but in this case maybe I use this correlation, I could use different types of correlations which are available in literature. This is how we calculate the values of the specific impulse. Now, one last thing I should also qualify for these impulses, because you will recall we talked in terms of some scaling law. I call that scaling law as Cranz-Hopkinson scaling law. We did this for Kranz, what was the scaling law? If you say I deposit some energy in some particular medium, I say I deposit some energy such that the equivalent explosion length is r0, and at some distance from this explosion site, let us say that the magnitude of the pressure spike is, let us say, or the pressure or the overpressure is Ps minus P naught at a point, let us say r is away. Then what was the Kranz-Hopkinson scaling law for overpressures? We say if I have an explosion, let me use a different color chalk. If I have at a similar site a similar explosion for which the explosion length is lambda r naught, then at a distance, let us say lambda r is away, that means the explosion length is increased by a factor lambda, and the distance if I increase by the same particular value of r s, then at this particular distance r is away, well, the magnitude of the overpressure is the same. That means an observer stationed at a distance lambda r is away from an explosion of explosion length lambda r naught feels the same overpressure as an observer standing at a distance r s from an equivalent explosion or from a similar explosion of explosion length r naught. This was the Kranz-Hopkinson scaling law for overpressure. Can I write a similar scaling law for, let us say this was for overpressure, can I write for impulses? And if so, is it exactly the same or is it different? For this I have to go back and ask myself how the distances change with explosion length. Let us do this particular problem. Let us say, well, I have the explosion taking place, let us say over here. I have maybe at a distance r is away, I have maybe a value wherein the pressure spike is so much, the explosion comes over here, pressure jumps by this, when the explosion length is, let us say, r naught. Now, if my explosion length is increased, what is going to happen? The same pressure spike, I will get r s by r naught is still the same, I will get the same value of spike at a distance lambda r is away. In other words, in this case what is going to happen? If I am going to take a look at r s dot or Mach number, or let us say the pressure ratio, I start with a high value of pressure, it decays like this in this particular case. In this case, since I have increased the energy or increased the value of lambda r naught, well, the blast wave will decay a little slowly, that means it will take a longer time. In other words, all what we are saying is, supposing I have an energy release E naught, I have a Mach number, let us say ms1 formed at a distance r is away. If I release higher energy, let us say I put more energy over here, the same Mach number ms1 is at a larger distance from the center over here, and if this value is r naught and if this value is lambda r naught, well, I have the same ms1 at a distance lambda r is away. Therefore, the distance from the site increases. If the distance increases, well, the arrival time increases by the same factor lambda Ta from an explosion length of value lambda r naught. If the arrival time increases, let us take a plot at the value of the impulse. That means initially I had at Ta the value of pressure going up, this is my ambient pressure, it came like this. Now, what has happened is the lambda Ta, that means the pressure spike came over here, it came over here, and therefore, what is going to happen? The time scale of the duration of the positive impulse, which is over here, also scales in the same way. This was t plus over here. The distances have increased, therefore, the times, because the same value of the velocity is now decreasing by the same amount, therefore, this time t plus is equal to lambda into t plus. If the time increases, well, the value of the impulse, if the value of impulse at a distance r s from the site of an explosion of explosion length r naught is equal to, let us say, I plus, and if now I consider an explosion of length lambda r naught at a distance r s value, the impulse will go by lambda times. That means the impulse scales as the explosion length lambda, and this I show in the slide, and let's take a look at this. This is what I show here. If I have an explosion of explosion length r naught, then at a distance r s I get an overpressure delta p, and I have an impulse I plus over here. The arrival time is lambda a, and the impulse acts over a time, let us say, t plus over here, T a to T a plus t plus. If I have an explosion length whose value is lambda r naught, that means I increase the value, and now I look at the impulse, that is lambda r s away, such that r s by r naught is same in both the cases. Well, the overpressure by the Cranz Hopkinson rule is still the same, but then my duration, the arrival time here is lambda T a. The value of the time at which the pressure falls to a value p naught is lambda T a plus lambda T plus, this is equal to T a plus T plus. Therefore, the magnitude of this impulse will be lambda times the value over here. That means Kranz-Hopkinson scaling law for overpressures is that an observer feels an impulse which is lambda times the impulse observed by an observer who is standing at a distance r s away when the explosion length is r naught. Here in this case the explosion length is lambda r naught, that is, the impulse scales directly as the explosion length for similar scaled distances, and this is what is the Kranz-Hopkinson law for impulse. Well, this is all about impulse, which we will look at. Maybe we will try to solve some more problems as we go along, but let us turn our attention. Are there any other effects of an explosion taking place? What are the two effects which we considered? We considered maybe overpressure from a blast wave driven by an explosion, which literally crushes the object because of the high pressure behind it. We also talked in terms of impulses, that means momentum which really drags the object. Now, in addition to this, whenever an explosion takes place, let us say I have an explosive, it is contained in a casing, let us say this is the casing, which contains some element of the explosive over here. The explosive is burnt, or it produces high pressure, and what happens? The casing ruptures. The casing ruptures, and because of the high pressure and velocity, the casing travels, that means the broken casing travels as a missile. It travels at high velocity, and if somebody is standing over here, the object hits him, and maybe when some object like iron or a fragment hits you, well, you feel the punch of it more than what an air pressure could hit you. Therefore, in addition to overpressure and impulses, you also have the missile effects from the explosion. That is, the fragments which are broken off from the casing could come and hit you. It is not only these fragments or pieces from the casing which break and come and hit you as missiles. If I have, let us say, the casing over here, and this explosion takes place, and there are some objects which are littered, like I say, let us say I have some table over here, or say I have some chairs over here, some other objects, maybe some pieces of earth or something which is lying over here. What is going to happen when the blast wave travels forward? This blast wave is also going to drag these things and give them some velocity, and also these particular things will also act as missiles. That means, from the casing I form fragments which are hurled as missiles. I also have the neighboring objects which are there, which are accelerated by the blast wave and come and attack a person or impinge on a person as missiles, and therefore, we can tell ourselves, well, the casing, I form fragments in the casing, and if this casing, let us say these fragments have a mass m and they travel with a velocity v, the momentum is mv, and when this momentum is brought to rest, well, I get a force and that causes injury to people who are standing. In fact, fragments sometimes do much more havoc than overpressure and impulses. Well, these fragments can be classified into two cases. I could call them as primary fragments. Primary fragments are fragments generated from the casing of the explosive itself. When the neighboring masses which are accelerated, I call it as secondary fragments. Well, what do the military people do? Or what do these terrorists do? In the explosive, they put some objects, maybe some shaped objects, like let us say nails, or let us say some lead shots or some material. This is put in the explosive, or they put these objects over here which are known as shrapnels. And when an explosion takes place, these particular shaped objects or the shaped objects over here travel at high speed, and they sort of produce lot of damage, not only on buildings, on human beings, on living things which are around the place, and we talk in terms of fragments, missiles and shrapnels in the case of an explosion. Therefore, our aim is, let us now do a small problem. Our aim is to find out what is the momentum which something, let us say I have this duster in the region around it. I call this duster as a secondary fragment. I have the shock or the blast wave which comes. This is made to fly off at a high velocity, and when this hits some object, well, it transfers a lot of force to the object, because it is traveling at high speed, it is brought to rest, I have a force, and this is what causes the damage. Therefore, let us try to get the missile effect coming out. Let us do this particular problem. I want to calculate the velocity and the momentum. Let us make some assumptions as usual. To be able to solve a problem, we need to make some assumptions. Well, let us assume that the blast wave which is produced from the explosion is spherical. That means I have a thing over here, I have a casing over here. Inside the casing, well, I have the explosion taking place over here. That means let the mass of the explosive is, let us say, ME over here, that is the mass of the explosive. Let us assume that the mass of the casing which holds the explosive has a mass, let us say mm, that is the mass of missiles which is formed. The total mass of missiles which is formed is equal to mm. Well, mind you, this all gets fragmented, is thrown in different directions over here. Therefore, we say, well, I assume a spherical geometry. Then I assume that the mass of the casing is mm, and I want to calculate what is the fragments, what is the velocity they have from this. It holds an explosive me kg, let us say. Let us also assume I want to find out the energy which is released. I say energy released from this particular explosive could be, let us say, U so much joules per kilogram is the amount of energy which is released from this particular explosion. Let us also assume that since being center and velocity at the casing when the thing just burst is, let us say, at the casing the velocity of the gases is v. At the center, since it is symmetrical, the velocity is 0. Let us assume that the velocity varies linearly from v to the value 0. That means, the value of velocity along this, when the thing explodes at the edge over here, the velocity is v. At the center, let us the velocity as a function of this particular distance. At the center, because of symmetry, the velocity is 0 over here. And with this, let us try to write an expression. The expression we can say is, well, the energy released from the explosive provides the kinetic energy for both the gases which are being given out and also the mass of the casing, which is totally the total thing which goes out with the same velocity. Let us assume that the fragments here also leave with the same velocity with which the gases are leaving. Therefore, the kinetic energy of the fragments from the casing and the kinetic energy of the gases is equal to the explosive energy which is released. Therefore, with this type of scenario, let us try to calculate the velocity. Let us write the expression down, the total energy which is released. If the energy released is U joule per kilogram, I have mass of explosive which is me. The total energy which is released is me into U, so much joules of energy is released. And where does this energy go? Into kinetic energy of the gases and kinetic energy of the fragments of the casing, and therefore, let us say kinetic energy of the casing, that is the total mass, is equal to half m into v square, that is the velocity with which the fragments leave the explosion site, that is at the time of starting it is v square, which is the same as the gas velocity. This is, let us say, of the mass of the casing as it is, or let us say the missiles water form. Kinetic energy of the gases is equal to half into mass of the explosives which form gases now into v square, that is over here. At the center, well, the velocity is 0, it is 0, therefore, the average kinetic energy is equal to half into me into v square, and therefore, I can now write me into the value, this is the total energy, is equal to half mass of the missiles formed from the casing into v square plus half into mass of the explosive which is generated into half of into v square divided by 2, me v square by 2 into half of this. This becomes my general energy balance equation. This is based on the assumption that, well, we say at the center the velocity is 0 because of symmetry. The velocity here is v, and the casing travels with the same velocity v, and it is broken into fragments over here. This is the total mass of all the fragments put together. Let us solve this equation. Let us see whether I can get some numbers for it. Let us calculate the velocity. I solve this, I want to get the velocity of the fragments v. Therefore, I tell myself, well, me into v square is equal to, I get v square me into u, I am sorry, this is equal to the energy per unit mass is equal to v square divided by 2 into, I get the mass of the total number of fragments which are formed plus me divided by 2. Or rather, I am interested in the velocity, therefore, velocity is equal to 2u, let us calculate v square is equal to 2u, and now if I were to put this down, I will get me on top and I get mass of the missiles which are formed into me divided by 2, or rather I took 2 over here, that becomes 2u, I have me over here, and I just write this down, or rather I get the value of velocity as equal to 2 into u into, I get, let us divide it by one way or the other, let us divide it by therefore, I get me explosive divided by into 1 plus, that is the mass of the missiles, into 1 plus half into me by and this also becomes half, that is, I take the square root of this. Now, if I look at this particular expression, you had units of, let us say, energy released per unit mass, therefore, the value of 2u has units of joules per kilogram. The value of joules per kilogram, I can write joule as equal to Newton meter per kilogram. Well, I can write Newton as equal to kilogram meter per second square into, I have to complete this, meter per kilogram. Therefore, kilogram gets cancelled, this gives me meter square by second square, or rather the units of this particular factor which is getting multiplied over here has units of under root this, that is meter per second, and since it has units of second, it is given a name, it is known as a Gurney velocity, Gurney, Gurney velocity. This is indicative of the energy in the explosion, and this multiplied by this gives me the velocity of fragments. And mind you, these velocities can be very high, and if the mass, if I have something like an ion which is getting accelerated compared to a plastic whose density is much lower than iron, since iron has a heavier mass, the mass into the velocity gives me a high value of the momentum, and this momentum when it hits an object is capable of piercing and causing misery to people. And this is how we say, well, these are the missile effects from fragments, from shrapnels, and also from the objects which are flying around that, which you call as secondary fragments. Let us go further. Let us try to do a small problem in this such that we calculate some velocities. Let us do this particular problem. Let us calculate the velocity of fragments for the case of the problem which I consider. I have an explosive of, let us say, mass 5 kg, whose energy per unit mass is, let us say, 4500 kilojoule per kilogram is the energy. Therefore, the total energy of this explosive is 5 into 4500 kilojoules. Now, this particular mass of explosive is contained in a steel shell over here. The mass of the steel shell is, let us say, 0.5 kg. The total mass is 0.5 kg. I want to be able to calculate what is the velocity of the missiles or fragments which are formed from the rupture of this case, and what is the velocity with which it emerges out of the explosion. I am interested in V. Therefore, I say, well, I have just derived the expression. I know that the velocity is equal to the Gurney velocity 2 into small u into the value of me by mm, mass of the casing, whatever is flies over here, into 1 plus me by mm into 1 by 2 to the power half. This is my velocity, and therefore, if I now put the value of Gurney velocity, I have 2 into u, which is equal to 2 into the energy is 4500 kilojoules. Mind you, I said to be able to get the velocity back, I have to have joules, therefore, it is 1000 joules into the mass, which is 5 kg, that is 5 into 4500 is the energy in kilojoules, into 1000 is joules. This is the value of 2 u, and this comes out to be equal to 6708 meters per second. This is the Gurney velocity, and then I calculate the velocity over here. V is equal to 6708, which is equal to the value of under root 2 u into, I have mass of the explosive, which is 5 kg, divided by mass of casing, which is 0.5, divided by 1 plus half into 5 by 0.5, this is 10 over here, to the power half, and this gives me the value as equal to 6708 into 10 divided by 6 to the power half. The value comes out to be 6708 into this factor, which is equal to 8660 meters per second. You find that the velocities are indeed large, and therefore, if an object at this high speed, we are talking of Mach number of this, if I calculate with respect to the condition of the sound velocity, which is something like 330 meters per second, we are talking of Mach numbers which are extremely high. Divide by 300, what is it you get? Something like Mach number 200. That means extremely high speeds, and these impacts on somebody, maybe even at some distance, mind you, these things will by drag it will decrease in velocity, but if it hits a human being, well, it just penetrates into his skin and causes misery. Even if it hits a building, well, due to the impact, the building may get damaged, and this is the effect due to the missiles. Let me take you through one more example, and this example I will show in a slide, and this example we have already done while looking at the different types of explosions. We take the example of the Texas City disaster, which happened on April 16, 1947, what was this? We found that the hull of a ship in this case carried something like 7,700 tons of ammonium nitrate, which was a fertilizer grade. We called it as FGAN, fertilizer grade ammonium nitrate. And when it exploded, well, we said that the type of explosion what we had caused something, the sound could be heard from this explosion over a distance of something like 450 kilometers away. The windows of buildings got broken over a distance of something like 40 kilometers away, and that was the type of explosion what you had. In this case of this explosion, I want to bring out the missile effects. This particular ship was berthed over here in the sea using a few anchors. The one anchor, the main anchor was 5 tons, and what is an anchor? You have a ship. Let's take a look at what we want to do. We are taking a look at the missile effects. You have the ship over here. Well, it drops an anchor such that the ship is berthed over here, it does not move over here. You have a auxiliary anchor, which is in this case is 2 tons, so you have a main anchor which is 5 tons. And what is happening? What happens to the anchor? You have an explosion taking place over here. Because of this, well, this becomes an object in the vicinity of the explosion. That means it is something like a secondary missile which could be formed, or a secondary fragment. And in this particular explosion, if I were to go back to the slide, the anchor, which is 2 ton, was hauled over a distance of 2.61 kilometers away. That means from the site of the explosion, it travelled a distance of 2.6 kilometers, and it formed a crater of 3 meter deep. Well, we will look at craters a little later. The main anchor, which was 5 ton, was hauled over a distance of nearly 1 kilometer. Mind you, a huge massive object being pushed over a distance of something like 1 kilometer away, or something like 3 kilometers away. This is the type of havoc which an explosive can cause. I just took this example because it illustrates the type of effects due to the missiles. Therefore, what is it we have done so far? Let us quickly review before we go into the subject of craters, because inadvertently we found one of the missiles formed a crater. We will look into it, but before we do that, let us therefore take a look. We are by now we should be absolutely clear what we mean by a blast wave generated by an explosion. What is the thing? It starts off at the site of the explosion, travels at high speed and gradually decays, and therefore time versus distance has this particular characteristic. We talked in terms of different types. We talked in terms of constant velocity. We were able to get the Mach numbers. Using that, we derived in the near field, wherein I have a strong blast wave, I was able to calculate the value of overpressure. I was also able to calculate the impulses. Similarly, when it blast wave decayed, we said, well, it decays at the values when the Mach numbers are little lower. I again calculated these values. These were the overpressures, which all of a sudden increased in pressure, that is, there is a compression process, and this, when something is over here, it literally crushes and damages the object. Well, the wind effect is associated with impulse, and it moves the object. Maybe it tilts the object, maybe it topples this. Maybe if I have somebody riding or somebody walking on the road, the impulse topples him down because it drags him and pushes him. Well, these were the 2 types of destructive influences which we talked of, and the third one we say is the missile effect from fragments, and also shrapnels which are done. These shrapnels, unfortunately what happened is, what happens is maybe people put some nails which have these, a nail has a point like this, which has a head over here, and when it hits, the nail can again puncture your skin and does damage, and these are things which unfortunately some people use to inflict damage on human beings. Well, these are the 3 effects, and now let us come back to the last part, namely we said, well, something goes and hits something, well, a crater is formed. What do you mean by crater? What is the effect of crater, and how does a blast wave form a crater? This is the last one which we do. Let us take a look at this particular example. Let us say I have the earth over here, let us say it is wet earth over here, loose soil. Maybe I drop let us say a marble or a ball over here, I form something like a dent on this. You know, if I drop an object which is spherical, I form something like a dent on this. Well, in the case of this, we just say is well a dent which is formed on the earth or somewhere on a loose soil. When a blast wave hits the earth, something I have the earth over here. Let us say I have an explosion taking place, I have a spherical explosion taking place, I have a spherical blast wave which travels into the earth, let us say. Now, when the blast wave travels, what it does is it compresses the earth over here, and you have such a huge compression, that means if the blast wave is strong, I have a huge compression, it strains it, it compresses and makes it strain such a value such that it gets into the plastic state, and then what happens behind the blast wave? Let's again put one more figure. I have a spherical blast wave over here, I have the earth which is being compressed over here, it gets into the plastic state, and once the earth behind the blast wave, I have the expansion fan, that means I have the pressure reducing over here. These, when the earth gets into the plastic state and crumbles, that means I have fragments of the earth which are available, and because of the pressure decrease, all these things now have a velocity. Because of the low pressure, it goes up, these are all thrown up, and these things fall back over here, and therefore what is it I am going to get? If a blast wave strikes the earth, that means I have the earth over here, I form something like a earth is removed, the earth is thrown up, I have a lip over here which is formed, I have something like a crater which is getting formed, and this is what we call as a crater, that is the crater diameter is let us say d naught. Because of a blast wave, the earth is thrown up, the low pressure behind it, it is thrown up, it accumulates here to give me something like a lip over here, and this is what we call as a crater. You know, we just dealt with it in a simplistic manner. All what we are saying is, well, the surface of the earth is hit by a blast wave and it forms something like a crater over here. And the lip of a crater is due to the falling of the debris which is thrown up, and some of the debris falls into the crater again. We keep talking in terms of different types of craters. We say on the moon we have craters, we say well Mars has a lot of crater, Mercury has some craters. Well, even on earth we have craters, you know, and these are all filled with water today, and they are used as lakes. We will take a look at examples. But what really causes the crater is maybe the blast wave. You have a blast wave which is coming and which creates the loose earth, which flies up because of the rapid expansion behind blast wave, and that is what causes a crater. To be able to qualify it, I take the example of another example which we talked of in our second lecture, that is at Chelyabinsk, wherein we had the comet entering the earth's atmosphere at high speed, and at high speed it enters, a blast wave got formed, and this blast wave could hit the earth, or else the comet itself could come and hit the earth, and when something hits the earth at high speed, I have a blast wave which is associated with it just ahead of it, and that forms a crater. In fact, in this particular case, you had a piece which hit a lake known as Lake Chebarkal, and in this lake also there was a huge indent which was formed. It was, mind you, it was frozen, and you had something like a crater which was formed. Well, in the next example, in the same one, I just showed this, a blast wave being formed. It is instructive to calculate what is the energy which is released, what is the type of blast wave which is formed. When at the surface of the earth some energy is released, we call it as a surface burst of energy over here, or if I have the earth over here and over the air I form a blast wave, and this blast wave creates a crater, we say, well, I have something above the surface of the earth wherein the energy is getting released. I could also have something like a buried explosive, That means, I have an explosive over here, I have something like a buried case, in which case maybe the explosive forms a crater, and it is to be expected that if I have a buried explosive, maybe it will create a larger one, but if the depth of burial is such that the explosive is very much deep inside it, it has to remove the earth from this particular place. Therefore, the effectiveness or the width of the crater or the depth of the crater which is formed, as the depth increases, maybe I say the diameter of the crater which is formed as d0, well, the d0 will increase as the burial depth increases, and then maybe it will come down. Well, the diameter of the crater goes as the energy which is released, therefore, it is proportional to the explosion length. And second thing is, in addition to diameter being dependent on the explosion length directly, the depth of the crater being somewhat, let us say, spherical, the depth of the crater is always a function of diameter, and this depth is approximately around like diameter of the crater to the power divided by 3. Well, this is all about craters. We'll quickly do this example of this Chelyabinsk type of an explosion what happened. We considered, well, this was on, as we said, this was on 15 February 2013, earlier this year. You know, the velocity with which the comet entered the atmosphere was around 18.6 kilometers per second. The diameter of the particular comet was around 17 meters. We can estimate the mass of this comet, assuming that the density is typically of a comet is around 0.6. The mass of this comet, if I calculate, comes out to be 15.43 into 10 to the power 6 kg. Mind you, the velocity is high. It is travelling with a velocity of 18.6, therefore, it has a huge kinetic energy, and this kinetic energy, when it enters the atmosphere at some height, is getting reduced. Therefore, this dissipated kinetic energy is what drives the blast wave, and some remnants of this come and hit your particular ground and they form a crater, and this is how we calculate. Let us say that the kinetic energy of this, assuming that the entire velocity is available, works out to be a huge number, something like 2.67 into 10 to the power 15 joules. That is the huge energy, which is something like it is something like 40 times the value of the energy released in the bomb which was released over Hiroshima and Nagasaki. Therefore, you have huge blast waves which are formed in nature, and some of the pieces which come and strike the earth, they create craters, and these craters have a diameter which is directly proportional to the explosion length. Well, these are the different aspects of the blast waves. We have considered the overpressure, we have considered the impulses from blast wave. We also talked in terms of the missile effects, and using these three, in the next class what we do is, we will address ourselves on the problem of how do I assess the damage, because even when a blast wave strikes the particular earth over here, you know, there is something like a shock wave hitting the earth, the pressure, that is the reflected pressure, is going to be higher than the incident pressure. That is, we are always looking at the side view pressure, namely the value of Ps, but the reflected pressure could be higher and it could cause further damage. Therefore, let us take a look at how to look at damages caused by the blast waves. Thank you.